Good morning. Here we are at last. It's the physics video lecture. Physics 105A video lecture 1. My name is Carl Rundy and I sent out the syllabus. Everybody should have a syllabus in front of them. And what I'm going to do is go over that and explain procedures for the semester. And then we'll actually launch into some material. So yeah, this is Physics 105A Classical Mechanics. My name is Carl Rundy, and it's all going to be video lectures and email, or primarily that. So I'll put my email here, which you already have. And let's see what we have on our syllabus, just to get started here. So I keep them very minimalist. So again, there's a phone number and my email. Office hours, it says by email, okay? So if I seem to not respond to an email, just try again. I have a couple of 100 emails per week now, but it doesn't matter. We're gonna get through this. In fact, we had a pretty successful semester last semester, so I'm completely optimistic and you guys should be confident that this is all going to work. Okay, so I'm saying next we're going to have 3 video lectures per week available at the YouTube channel, and the Physics 105A playlist is where I'll drop them all. And the homework assignments are going to be announced in the video. So actually, in the course of our lectures, I'm going to put homework assignments on the board, and I'll often start them off for you, and they'll be embedded right in the material that you need to know to do them. So that also works pretty well. And there is no textbook. I have some books here that I've used in the past. I'm going to list some books, but there's no required text for the class. Nonetheless, these are some recommendations. You can buy books used. You can borrow them, buy them used. And it turns out you can get used books for pretty cheap, and you can get a whole little library of books for the cost of a brand new one. So anyway, in the past we've used ARIA. That's this gray one here. I don't know what the current edition looks like, but Classical Mechanics by ARIA. We've used Fowles. And these guys often end up with a second author or a third author over the years because there have been many editions. Marion and Thornton. So Marion is a highly regarded book, and there's a more recent one by an author named Taylor. And I loaned mine out to somebody, I never got it back, so I don't have that. Taylor is a big red cover, pretty thick book, excellent book. So these are all good books, and there are many more because this subject is very mature. And I'm just going to unfold a certain program, and that brings us to our next topic of notes. So I have here, under homework, pictures of your handwritten lecture notes and worked homework problems sent to me by email every Friday evening, no later than 6 p.m. So every Friday you're going to send me 2 emails in which you've taken pictures, first of all, of your notes, your lecture notes, and second of all, of your homework assignments. For the homework, it's best to use some kind of PDF file converter in order that I have something that I can really read and print out. But for the notes, typically a good camera nowadays on a phone or something gives excellent pictures. So the notes, I just want to see that you did them and check them off. Good. So as far as the notes are concerned, there we're making a virtue of necessity. So our ambition is to get some really good lecture notes. Okay. Under these circumstances, you've got the videos, I'm supplying the material and the logic. When you take your notes, ideally you leave a lot of space. because you can return to them and fill things in and just turn those notes into your book, so to speak. So the notes are very important, and you know, you're being given credit for the notes as well. Okay? Notes and the homework both receive credit. So those lecture notes, and then of course the homework problem sets, I'll just write problem sets that are going to be written on the board as part of the notes, and that you're just going to, you know, write on separate paper and turn into me. Both of these, when you email them to me, so you email them, always open a new message, so that keeps them from getting lost. Always open a new message, and your new message is going to say your name, and then physics 105A notes. And then the other one's going to also say your name, physics 105A homework, abbreviated or not. Okay, so those will be two separate emails every Friday by 6, one with your lecture notes, one with your homework. Very important that you put the class in there and your name, and then it's notes, because I have all my classes doing this, and you know, hundreds of them are coming in. But like I said, it worked last semester, it's going to work this semester too. Good. What else? So then we have a midterm exam, and there's a date for that. That's going to be very standard. I mail it out to you. You mail it back to me in a couple hours, or 1.5 hours or something. And then I've got the grade scheme here. And 15% for notes, 15 homework, 25 for the midterm, final exam, 45%. Any curving that I do happens at the end of the semester when all the grades are in, when all the things are in. So you're just worried about doing this the best you possibly can at this point, you know, and collecting as many points as you can. But you know, whether you fall into these ranges, will, you know, we can make adjustments to that, but only at the end of the semester. Good. So you see, that takes us through this short syllabus pretty rapidly. Let me see if I have some other topics for us. Talked about the books. Yeah, well, next I'm going to do an outline, a short outline of the semester material, and then we'll actually get into some material. And by the way, any questions on this, you know, just save them for later and email me, and hopefully everything will become clear. For starters, again, we are sending all emails to this email address. Always open up a new message, and then for your notes, your name, physics 105A notes, and then for the problem sets, your name, physics 105A homework. And that should get us started. Okay. Okay, let's go ahead and send this up and talk a bit about the material. So this is Newtonian mechanics, and we're going to pursue it on a more formal level than you've seen before. Some really interesting mathematical topics along the way. And our ambition is really to prove everything that we do. Even if we go back to some mathematical theorems, say from calculus, sometimes we throw the proof up on the board as well, just for practice. So let's let's kind of outline what we're doing here. So I'll just write Newtonian mechanics. Mechanics of a point particle. So generally it's just one object that we're pursuing. So Newtonian mechanics of a point particle, and you guys have seen, of course, Newton's law of motion. So the mass times the acceleration is equal to the net force. And there's a lot going on here also formally, because what's an acceleration? Okay. Second derivative of a position, And with or without the little arrow, talking about vectors. So what's a vector? Okay. And then the claim here is also that force is a vector. And finally, there's this expression of the mass. So there's a lot of background in this and a lot of formalism that one can and will study. But what we'll do is take this, first of all, one-dimensional motion, and then we move on to forces that involve a potential energy. So I'll just write potential energy here. And finally, we get to the subject of small oscillations, which actually seems pretty endless during the semester. We spend a lot of time on small oscillations. And then we move on into motion in 3 dimensions. So I'll just write motion 3D. And finally, it culminates in the central force problem. So I'll write here the central forces and the Kepler problem, the actual two-body problem of orbiting planets and satellites and so forth. So central force and then the Kepler problem. And you know, you've heard of Kepler, you've heard of Newton's law, you've heard of orbiting planets and satellites, you've heard that the orbits are ellipses and those types of things, but you probably have not seen the proof. We're going to develop this very rigorously all the way to the actual proof of Kepler's laws, which is kind of a high point in your education, important point. So yeah, we're doing that, through the Kepler problem. In addition to these things, I'm just going to write here, we also have mathematical topics that we spend a fair amount of time on. And one of them is just kinematics in different coordinate systems. So kinematics in plane polar, well actually let's go ahead and list all 3. So kinematics in Cartesian coordinates, plane polar, spherical polar. So Cartesian coordinates, plane polar coordinates, etc. Another important topic of just mathematical method is the Taylor expansions. Experience shows that people have seen this, but they haven't really practiced it, so we get a lot of practice. It's one of our major tools. So Taylor expansions, complex numbers, and functions. So if we have enough time, we can extend the discussion of complex numbers into complex functions and what I'll just call complex analysis, or complex, yeah, we got to call it something, analysis, if we have enough time. Yeah. It's a pretty ambitious program, but we can do all this. Okay, so next I'm going to, this is a brief outline, got some books. I'm going to return to these concepts here and actually go back to some really basic type of material that you would have had at the beginning of 4A, namely the laws of free fall, what is a vector, because eventually we just inherit Newton's law and declare that this is our foundation and move on from there. So we want to spend a little bit of time in developing how these concepts were even discovered. Okay. So and that'll take us, so here we go. So that we can fill the rest of the hour with. And it makes a bit of a review as well. I'm just going to describe what I often do as demonstrations. I'll just describe it in words and gestures. So we're beginning now with the kinematics idea, motion. And we need the concepts of position, displacement, velocity, acceleration. Okay. But where do those even come from? Why do we need those and not some others? So I'm going to actually begin with a question. What is the nature of falling motion? Falling motion that of course then turns into free fall. So what is the nature of free fall? And the demonstrations I do in an experimental type of class is dropping the hammer and the feather. Okay. So I'll just write here demonstration, fall of the hammer versus a feather. And what you learn when you investigate this is that you have to eliminate friction somehow. Without friction, the hammer and the feather fall exactly the same. And there are interesting ways of demonstrating this. For example, you can take a big, heavy textbook and drop it, falls just like a hammer, okay, falls like a brick. You can drop a feather, just floats down. You can put the feather on the book, drop it, and that feather will just, it won't stick to the book, but it'll fall with the book in exact free fall. Okay. So these demonstrations of the fall of hammers versus feathers versus books, etc., teach us that all objects fall the same if the friction can be minimized, or we could say all objects fall the same in the absence of friction. Okay. So these demonstrations lead to the conclusion: all objects fall the same in the absence of friction. Okay. And it's also a matter of degree. If you can make the friction negligible, then it's all as though it weren't there at all for all practical purposes. Okay, so those are judgment things. I won't go into that anymore. But the strict statement, all objects fall the same in the absence of friction. If you eliminate the atmosphere one way or the other, you get the law of free fall. So that is what we call free fall. That's a condition where everything falls exactly the same. So here, I love to number things. The second point then is, what is the nature of free fall? Now that we say that the hammer and the feather and everything in between falls the same, what is the nature of free fall? And we define that as free fall. So nature of free fall, question mark. What is the nature of free fall? And that's where Galileo made the crucial progress, crucial discovery. He was able to characterize free fall in terms of kinematic quantities. Good, so let's go ahead and pursue that for a bit. What do we have here? So what I'm going to do is describe a so-called drop chord demonstration that you guys can do on your own at home. nature of free fall. So here we are with Galileo. Now Galileo, as far as I know, worked with an incline. And he rolls things down the incline and they pick up speed. Just like when you drop something, it picks up speed. So he's rolling a ball down the incline, and I'm going to draw it with these progressively greater separations because it's picking up speed. And what he does is he mounts some little object in the groove in his inclined plane that will make a clicking sound, and he can slide those along, and you release it from rest, you get, here, let's be a little back. Imagine we release it from rest right here at the top. We release it from rest right there. So there's our first click. Okay. So we get his click. I'll put this a little further over here. So Galileo's got the incline. He releases some kind of marble or ball bearing or what have you. It hits these things and you get a click, 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 click. He adjusts the separation distance until the clicks are perfectly rhythmic. Perfect rhythm, 1, 2, 3, 4. Okay. And what we can do, since it's a little complicated to construct an incline, is do a drop chord. So if you've never seen this or never done it, this is a great little home project. With the drop chord, you've got a string, and down here, you anchor it with something. I usually tie a knot in the string and anchor it with my pen. But the string, the bottom here of the string is on some kind of soundboard, like a cooking pot that you turned upside down or something. And you've got a string here, and then you put some clips. You can use paper clips or some kind of little notebook clips. And you put these clips here, and I'll put little stars. Put one more up there. So those are clips, and if you mount these clips with the right separation distance, when you release this thing, they're going to hit sequentially 1, 2, 3, 4, and more if you have patience. And again, it's going to be a perfectly rhythmic beat, but you have to increase the distances. Okay. So I'm not going to write anymore. I'm telling you how to do this. You'll find it really interesting if you pull this off. You do it with a 1.5 meter string or something like that. So the drop chord's got the same thing. Galileo did the incline. We can do the drop chord. And what is the lesson of this? When you do the drop chord, so let's go ahead and make a little table here. I'll call this drop chord data. You've got the distance fallen. And you've got the time. And let's leave another column there. So the time is just 0, 1, 2, 3, 4. You release it at 0, click, 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 click. Okay. But what you find for the distance fallen is in units of this first length here, little L. In units of this first length, you're going to, of course, have fallen 0 distance at the instant you let it go. You're going to get 1 unit of length, 4 units, 9 units, 16, etc. So for example, if this first unit of length is 10 centimeters, then you're going to get 10, 40, 90, 160 centimeters. If it's in inches, same thing. Okay. It's always going to be a multiple of that. So this is something you want to see and experience, because what you're looking at now are the data for the distance times squared law. Okay. So our data table here, so data star show that distance fallen proportional to the time squared. Okay, that's what these numbers show, and if you do it, seeing and hearing is believing. Okay, time squared, or I can say distance d is proportional to t squared. Okay, let's set this up. Continue on. Like I said before, you guys keep your notes really well spaced out, and they will look very logical. They'll be really good. Okay, so we're continuing this idea here. Now, this is one of the only times you can do an experiment and get this law of nature delivered to you, so to speak. So distance fallen proportional to the time squared, or, continuing here, distance fallen over time squared, right? Proportional means there's a proportionality constant. So equals constant. Okay. But what is this? Length over time squared, that's an acceleration. So because of this means that, what does this mean? This means that free fall motion, didn't even demonstrate it, but yeah, we're just talking about dropping something, okay? Just talking about dropping something. Free fall motion is motion with constant acceleration. Is motion with constant acceleration. And now I'm going to formally introduce the kinematic concepts, and I'll let you guys integrate them up. Okay. Constant acceleration, but for the moment, this is a law of nature, and it's really foundational for what we're doing. Okay. So it's so foundational, I'll put a couple exclamation points there. It means that free fall motion is motion with constant acceleration. And now I'll put the recall kinematic concepts, and those were what? Position, displacement, velocity, acceleration. Now, since we've already had this, and this is calculus based, of course, and you've already had it in that way, so I can write these down here. Position, I'll use vector r for the position. Okay. Displacement, I'll use delta r vector equals r minus r0, just the difference of two vectors. Velocity, v is the limit as delta t goes to 0, delta r over delta t, which is dr over dt. Notice I'm doing this in vectors already. We'll come back and make sure we understand what a vector is. And acceleration. And the acceleration, vector A equals dv dt, right? Derivative equals d squared r dt squared. Okay. So here's the thing. These are just definitions, you could say, kinematic concepts here, definitions. But we see that the acceleration, which is the second derivative of position with respect to time, has the units length over time squared. And we just learned that free fall is motion with constant acceleration. Okay? So the law of free fall is that the acceleration is constant. So we actually have everything up here. And let me set this up and I'll have you guys complete it as a homework problem of just integrating, you know, the antiderivatives of these expressions here in order to find the law of the general motion for constant acceleration. Okay. Good. Well, let's do that. So here, let's go ahead and call this homework problem. From acceleration equals constant, show that R of t equals R0 plus B0t plus 1/2 a t squared. Right? This is the formula for constant acceleration. You've seen it in terms of free fall when you put g in there. Okay, minus sign as well. Yeah, so how do we do that? Actually, let's call this part 1. And part 2 is actually really interesting. Show that this motion is restricted to a plane. Show that R of t is restricted to a plane. And by the way, this does not require a fancy calculation. It's really just a 1 or 2 line argument. You can even just argue it in words, okay? But experience has shown me that it's not trivial in the sense that people often fight around with this little problem for a while, but it's interesting. Motion under constant acceleration is restricted to a plane. As far as proving this, let's just get started. So we have dv dt is equal to constant, and a equals constant. So yeah, what if we integrate this or just get the antiderivative of it? Then we have integral dv dt is equal to integral a dt. And you know, we can go from 0 to t on both sides. And I'm going to put a little prime here because this is the time that we're talking about, and here here we just have an integration variable, right? Because we have boundaries of integration there. Okay. And you're going to then get on the right side is a times t, because this is a constant. You notice we're actually doing 3 integrals at once, because we're supposing we have 3 components of the acceleration. And you're going to get over here v minus v0. So that's one step, and a second step using the same argument here is going to bring you to this. So that's part of your first homework assignment. Since this is a Monday lecture, this one will be due on the Friday. Okay? And basically what we'll do is any homework assignments that come onto the board Monday or Wednesday are due Friday, and then subsequent lectures turn them in the next week. Okay? So you always have a couple days to do this. So that's a start. We've got ourselves a little homework problem. Let's see how we're doing time-wise here. Excellent. We've got nothing but time. Okay, yeah, this is the fundamental basic problem here in law of free fall constant acceleration. So you'll end up with this. We already have this velocity, v naught minus at. And let's look at Newton's law again. Okay. Let's look at Newton's law again. Since now we have these kinematic quantities and the law of constant acceleration, which includes the law of free fall. This wouldn't have to be a free fall acceleration. This could be a charged particle moving in an electric field, that type of thing. So it's very general. So we're going to go ahead and write Newton's law again. Contemplate it a bit. So once again, we're looking at mass, second derivative with respect to time, net force. So I've already just assumed the vector nature of these things. We're going to go into vectors in more fundamental detail, but I'm assuming what we know about vectors. But what about the vector nature of force? So next, we basically talked about kinematics and why this side of that equation is so important. So next, the vector nature of force. And so first of all, we want to talk about what force is independent of Newton's law. And for that, I have brought a scale to class. And the scale, it's just a spring scale, and it actually measures things in newtons. That's our unit of force. And I even brought a chunk of metal here. And on this scale, it's roughly 10 newtons. That should be visible. And I have a second scale. And it's also 10 newtons. Okay. Got to oil these things before you use them. Let's see here. Close enough. Okay. We're calling that 10. Good. So these two scales are reasonably equivalent. I can split the weight between these two scales and roughly get 5 newtons apiece. You guys are going to be seeing this and not me. Here, let me have a look first. Yeah, roughly. Okay, so we're roughly getting 5 newtons apiece. We can get 6 and 4, 4 and 6, adds up to 10. Now, the vector nature of force that I just showed you is what we call simple addition. And I'll just draw this thing here. We've got our scale, and it's reading 10 newtons. But if I hang this, I'm going to draw very carefully what I'm going to do. If I hang the string and suspend the scales like this, okay, these are the scales. What are the readings going to be? Apparently, I have 10 newtons pulling straight down. What are the readings on the scales going to be? Okay. Now, when you're not as sophisticated in this thing, you say, well, it's still going to be 5 and 5, but I'm going to make short work of that because I can get pretty much any reading I want. Okay. And you're probably seeing over 20, so 20 plus 20. How come I get a 5, instead of 5 plus 5, how come am I getting 20 plus 20? Okay. So that's the crucial demonstration for the vector nature of force. The reason is this, and let's just assume this was done to scale. These two red arrows add up to this black one here, and this was clearly the tension in the string. Okay. So what this vertical component is half of these 10 newtons. So I'm getting 5 newtons here, and if I just take this length, 10, 5, 10, 15, 20, and a couple, okay, this is literally the geometry that I just demonstrated to you. This is demonstration of the vector nature of force, and the same thing is happening on the left side. Okay. So force is a vector because the forces add like arrows. Literally, they're adding like arrows here. So we do have the vector nature of force from this drawing, and we have a couple of things. We have the vector nature of force, and of course this scale was just measuring weight. Okay, so the weight is an example of a force. Weight is a force. Okay, we measure it in newtons. Okay, so that's my vector nature of force discussion. And this is also the kind of thing you can play around with. All you have to do is have a string or chain or something tied between 2 points, pull down in the middle, and you can generate tremendous forces. If this were not 10 newtons, but your body weight, then if this were a chain or a rope, it could actually pull things together, break things. You can generate tremendous forces, and once again, it's, well, your Pythagorean theorem is going to tell you what this one here on the bottom is, but these two are the 5 plus 5 in the up direction that counter the 10 newtons down. And geometrically, just measure it off, and this would have been about, I'll just write 22 newtons, which is about what my scale registers before it bottoms out. Good. So we have the vector nature of force. The last thing I have to talk about is mass, but I may be running short on time. Yeah, this is a good time to next, what about mass? So what I'm going to do next time is discuss a really elementary dynamic situation that we usually do in our lab with a couple of masses using Newton's law. And then we'll have set this up pretty well. Where these concepts come from. We're doing really elementary things now, but that's a good way to set it up, and then we'll just get into all the technical details as the semester unfolds. So far, we're talking about Newton's law. That's going to be point mechanics is what the subject is. Newton's law of one-point particle. We've already discussed kinematics through acceleration. Law of free fall is a law of constant acceleration. in terms of Newton's law, it would be a constant net force, but we haven't quite gotten there yet. So yeah, we have discussed kinematics and where it comes from. The vector nature of this net force we just discussed here. And the example I give next time will tie these things together, and then we'll keep moving on. So, any questions you guys have, just fire me an email. But for now, I'll just remind you, you want to take really nice notes, leave a lot of space, so your notes just turn into a book. It's one of the goals of our semester. And you email me the notes and whatever homeworks you have done every Friday. And for example, the Friday assignment comes on next week's homework, but the notes will always be the Monday, Wednesday, Friday notes, Friday afternoon. Take some pictures of them, send them to me. And we'll be in touch. Okay. Have a good day.